Okie doke. Well, I will go ahead and get started with chapter 1 and 2, and we should be able to finish up today pretty quickly, unless you guys have questions along the way. Okay, so chapter 1, what is statistics? So, like I said, I'm going to try to use these comics to keep things mildly entertaining, but the real goal of this first chapter is to determine what is statistics and what kinds of statistics will we be looking at. So statistics is the science that deals with the collection, classification, analysis, and interpretation of information or data. So an important definition to remember for your first homework. So what makes statistics unique is its ability to quantify uncertainty and make precise. So this allows statisticians to make categorical statements with complete assurance about their level of uncertainty. So you're going to hear a lot of times we're going to talk about things being 95% confident. We're going to talk when we get to confident intervals, or we're going to talk about significance levels where alpha equals 0.05. If you're taking any statistics classes in the past and you do hypothesis testing, you'll see that we use this 95% confidence or 0.05 significance, where you get a p-value of or value being less than 0.05 means it's significant, and we can go on to interpret whatever that value is. So first example of a need for statistics, we have this this chart here. It has to do with the testing done before the Space Shuttle Challenger exploded. So the decision to launch in 29-degree weather, which in Florida is like very rare, so I could see how this could happen, but you see that this guy says, oh, that part of the curve. So if you don't have any test cases and then you want to move forward with an experiment, then you can't extrapolate past where the values were. So if it had been extremely hot or extremely cold, we did not have any example or way to predict that particular failure. So a little more positive example is the polio vaccine. In 1954, these vaccine trials were performed on some 400,000 children with very strict controls to eliminate biased results. So good statistical analysis of the results firmly established the vaccine's effectiveness, and today polio is very, very rare. So we'll talk a lot about bias in this class and different kinds of bias, particularly in sampling when we get to sampling. So we need to explain the difference between descriptive and inferential statistics. So data analysis, the gathering, display, and summary of data, probability, which we'll talk a lot about next week, is the laws of chance in and out of a casino. So odds ratios and probability of something happening, or the probability of a value being more extreme than a particular significance value. That's where probability really comes into play in statistics. And statistical inference is the science of drawing statistical conclusions from specific data using a knowledge of probability. So inferential statistics is the part where we're going to get talking about hypothesis testing, confidence intervals, etc. But the key definitions really are descriptive statistics describe sets of data, and inferential statistics draws conclusions about sets of data based on sampling. So the elements of a descriptive statistic. So the one or more variables that are to be investigated, which are characteristics or properties of an experimental unit. The population or sample of interest, which is a set of units that are of interest in studying. The tables, graphs, or numerical summary tools, which are ways to present the data. And the identification of patterns in the data, which are ways to infer the data. elements of an inferential statistical analysis. So one or more variables that are to be investigated, which are characteristics or properties of an experimental unit. Population of interest, which is a set of units that are of interest in studying. A measure of reliability for the inference, which is a statement about the degree of uncertainty. And the inference, which is an estimate or prediction or some other generalization about a population based on information contained in the sample. And the sample, which is a subset of the population. If you haven't taken the homework yet, you'll probably want to refer back to these slides. So, where can we get data from? Well, pretty much anywhere you can think to get data from. Published sources such as like newspapers, or not that anybody would do that anymore. Online sources, there's plenty of like government data or financial data out there that you can pull down to get data from. There's also designed experiments, which is more like, see that a lot with like agricultural type research, or like, you're growing tomatoes in one plot, and then you have another plot of tomatoes that you give some fertilizer to, and then so the first group is a control group, and the second group is the treatment group. That's a designed experiment, and then the data you get is what you collect on, how big are the tomatoes on the unfertilized plot compared to the fertilized plot. Or you can do an observational study, which is, you observe something in its natural element or environment, and you kind of, write down characteristics of it that you can then study and compare to another group. So,
Professor Davis?
Yeah.
So, quick question. Is there any type of resources that you should stay away from when collecting data?
Well, it depends on what your end goal of the analysis is. So, in business, we talk about designed experiments. Let's say you wanted to look at the effect of cigarette smoking on people's budgets. You wouldn't want to design an experiment where you had to force people to smoke cigarettes so you could see how much money they were spending on it, because it would become an ethical dilemma. So there's something like that. The best example I can give from a design experiment, which is why you don't see as many design experiments in business. As for published data, if it's online and it's from a legitimate source, so always check where the data is coming from. Let's say you're working with healthcare data. That's something that could be dangerous because there's some protective health information. So you either need to get de-identified data, or only work with the data that makes it where you can't identify a patient. Does that answer your question? Is there any other kinds of data you're particularly interested in?
Yeah, I mean, and just in general, like when you were talking about like published newspapers and some of these online resources, I've seen some that may, for lack of a better word, have a political slant where you can see data from different things that, how do you know exactly where they're collecting it from, and is it valid, good data?
I wouldn't have to look at that case by case. I mean, I was thinking more like you go into like financial data, you have to assume they're reporting those values correctly, or if you're in like a financial database like Capital IQ or something.
Okay, that makes more sense.
As for like data from a political standpoint, yeah, we're going to talk about bias at some point in this class, and I can talk more about that, how to avoid like sampling bias and ordering like surveys.
This is more driven towards like financial statistics.
Yeah, probably more that style of statistics, not political or survey type research.
Okay, very good. Thank you.
No problem. So the next question I wanted to bring up is, what's the difference between qualitative and quantitative data? Have you guys heard of these terms? So quantitative data are numerical in nature, right? Quantity means it's like some kind of number value. Whereas qualitative data is more like categorical in nature. So let's say we surveyed the class and asked what their favorite color was, and we had 3 people say blue, and 10 people say red, and 10 people say green, whatever. So we have 3 qualitative variables being the colors, but then we could get a quantitative value off of that by the number of people's favorite colors or something like that. So we're going to do stuff like that so that we can still analyze qualitative data with quantifiable methods. But quantitative data is more, a discrete or continuous variable that is numerical in nature, like somebody's weight or height or the number of chairs in this room, etc. So how do populations and variables differ? So if we have in this picture, we have a population of the state of Massachusetts. And then what we would do is we would take samples from that population and we would look at some mean value for each of those samples here. And then there's a test that we're going to do way later in this class towards the end called analysis of variance, where we could compare these 3 groups of means and say, are they different at a statistically significant level? But more from the definition, what you'll need for your homework. A population is a set of units of interest to a study, and a variable is a characteristic or property of the units being studied. So a population, a population is a set of units of interest to a study, and a sample is a subset of the units of a population. So what is a representative sample, and what is its value? Well, a representative sample is a sample that exhibits characteristics typical of those possessed by the population of interest. It is valuable because these characteristics allow inferential statistics to be applied. So we want to make sure, if we're doing like survey type research, that every group is represented at the way it should be. Otherwise, it will bring in bias. It could be oversampling bias if we have too much for one group, or undersampling if we don't have enough from another group, or we completely miss a group, so we have non-sampling bias. There's lots of bias that we could talk about, but we want to make sure that when we're running statistics that we use a representative sample to make sure that we can draw the right conclusion from the analysis that we're performing. So what is statistical thinking? Statistical thinking involves applying rational thought and the science of statistics to critically assess data and inferences. So that covers chapter 1. Mostly it's just defining terms and going over and outlining what the class is about. But now we'll continue to chapter 2, and we'll actually start using Excel and playing with some numbers and some minimal data analysis. So chapter 2 is methods for describing data. So what is data? So data are the raw material, or the numbers that we use, and then from that data we can create information by analyzing the data. So this chapter concentrates on data description. How can we represent data in useful ways, and how can we see underlying patterns in a heap of numbers? So how can we summarize this data's basic shape? Fortunately, our data does not come to us in a melon like that, but it can, and it requires lots of cleaning. So to describe data, the first thing we need is some actual data to describe. So let's collect some data real quick. So here is some real data as part of a classroom experiment from a 92 Penn State students reported their weight with these results. So we have two gender-based groups, males and females, and a set of data points of their different weights. So getting down to it, we can build something called a dot plot. 1 dot per student goes over each student's reported weight. So I think we have, 92 students. How would you describe the shape of this data? I mean, it's kind of a bell curve shape, kind of normally distributed, which is good. The averages seem to be kind of in the middle, around 150 pounds. There seems to be some extreme outliers, way above 200 and below 100.
So you would call this a bell curve?
I mean, it's not perfect. With the sample size of 92, we're going to learn something about the central limit theory and the law of large numbers. The larger the sample size that we take, the more this would approach a bell curve or a normal curve. But that's in a future class. But let's look at ways we could kind of describe this data. So we could use a frequency table, and we could divide the number line into intervals and count the number of student weights within each interval. So we have these class intervals or ranges, and then we would see how many students fall into that range. And then we would take that frequency and divide it by the total, and it would give us, the relative frequency of each of those kind of groups. So some guidelines for forming class intervals. This is also important for bin development, for doing frequency tables or certain kinds of histograms, but we'll come to that in a second. So use intervals of equal length with midpoints at convenient round numbers. Makes it a lot easier to input to a computer as well. For a small data set, use a small number of intervals. And for a large data set, use more intervals. So we take that data from before and we create this frequency table, and you can see it kind of looks kind of normal or bell shaped. Definitely see it's a little skewed to the left. But this bar graph is called histogram, and we'll learn how to make those in a second. So each bar covers an interval and is centered at the midpoint. The bar's height is the number of data points in that interval. So we can also draw a relative frequency histogram, plotting the relative frequency against the weight. It looks exactly the same. So you can see on the left here, that's just a count value. And on here, we have the relative frequency as the y-axis. So as our first example, let's complete this table. So I believe that I uploaded into the week 1 folder a work along Excel book. If you download that, then it should have that data already in. I'll make this bigger. I don't know if it makes a difference because you guys are online. And has anybody not used Excel before? Okay, I'll take that as a good thing, good sign. So we're going to use Excel to solve this this table. So we're missing a few values out of it. So the first one that we're missing is we're only missing one frequency, right? So we could do a very simple formula to replace that missing value. So if we use the equal sign and we multiply 400 times its relative frequency, it will give us the frequency for that particular range. Now to get the relative frequencies, we're going to get the ratios of those particular class or intervals to the total. So we take the frequency of the B range and we divide it by the total. We can get the relative frequency for that particular range. We can do that for each of these relative frequencies or class intervals, and it'll help us solve. And hopefully we do this right, and all of our values here should add up to 1. And you can see down here, it does. It sums to 1. There's 5 variables. It gives us the average is 0.2, but that's not particularly helpful in this problem. So hopefully that was a very quick introduction into Excel formulas. We'll get into some slightly longer formulas as we go through this class, but hopefully it's not too bad. So that should have given these values if you were following along. So our next example is we have some qualitative variables with 3 classes, x, y, and z, is measured for each of 20 units, randomly sampled from a target population. So we're going to use this data observed to complete several questions on that data. So I have example 2, chapter 2, part 2. So what we want to do is find the frequency for x. So I've converted this kind of block format to make it easier to use in Excel and just made it one column. So the next formula I'm going to teach you is going to help with working with more qualitative variables. So, you know, if we're using male and female or on and off or, you know, favorite colors, we can do something called equals count if, and then it asks for the range. So we're going to pull this whole range, and if it equals the class we're interested in, so if we click on this X, then it should count up the number of X's in that column for us. So we know that there are 8 X's based on that formula. Now the next thing, there's some cool little tricks you can do in Excel, is you can put $signs next to the A's and numbers, and that will hold that range static. We don't want to put it on the C2 because we want, when we drag this down, we want it to move to C3. So you'll see it iterated down from C2 to C3, so now it's automatically going to count the Y's. So we had to put the $signs in there to make sure that it kept the range the same. And we can drag it down again, and it'll give us the frequency of the Z's. So that gives us the frequencies, but we're interested in the relative frequencies as well. It'll help with making our charts in a second. So we want to, first off, make sure I'm going to do a sum formula. And we're going to add all these numbers up and make sure it's 20. Good. Because there should have been 20 in our little pair. So the relative frequencies are going to be just like we did on the first example. Number of X's divided by the total. And what we can do is now we can keep that E2 static with some $signs, and it should allow us to grab this handle here and give us the relative frequencies for Y and Z. So the next thing we're going to do is create a bar graph with our relative frequency. So we can do insert recommended tables, and say there's a column or bar chart, clustered bar, either way. And you just insert that chart, and it should create it for you. Not the most interesting data, but we can see that it creates a relative frequency bar graph, and it has 0.4 matches up, 0.35, 0.25. That is how you insert a bar graph. Now the other graph it's going to ask you to create is a pie chart. So if you go insert, you can do pie chart directly, but it actually also recommended a pie chart from the recommended charts, and that gives you a pie chart, which does a particularly good job when you're talking about relative frequencies because they add up to 1. So a pie chart is generally a pretty good visual representation of that kind of data. For looking at like your monthly budget to where you spend your money on different items, or your gas bill, your power bill, etc. You can pull it into a pie chart like this, and you can see where are you really spending the most amount of your money in a quick and easy visualization. Okay, so that should help you with the second question. I don't know if it breaks it down, but I am recording, so if you want to rewatch it, or is there any particular thing I can help, or what part am I going fast on? If you highlight your data and you go up here to insert, you can insert any number of different kinds of charts. All right, no worries. No, I'm trying to start at the very basic level of Excel, so I don't believe this class needs any prereqs, but just let me know if there's any other Excel-like based questions. There's a lot of YouTube videos out there too, if there's something in particular. I guess the basics of what you need to know in Excel. So from the home screen, when you open it up, you have changing different number types here. Insert gives you different ways. I don't think we're going to talk about pivot tables, but that's a super cool little tool. But I don't know that we really use it in this class. Inserting charts here, different equations, probably won't get that far in this class either. Formulas, so you can, if you have a big sheet of formulas, you can calculate options and calculate out sheets. Different data. So you may or may not have the data analysis here. I can show you how to open that up real quick because let's see, I think it's down in options, add-ins, let's see, Excel add-ins. So you'll need to have the analysis tool pack, and that'll make this data analysis option open up, which we'll use in a second when we get to kind of a quick shortcut to get all the descriptive statistics. But let me know if you need to see that again. Let's see, I think that's that. Also, this is all based on what it looks like from a PC. I don't have a Mac, so you'll have to Google if you're using a Mac on how to do different things in Excel that may not line up exactly as it does on what a PC looks like. All right, so I gave us an example of analyzing qualitative data and getting some basic frequency data on it. So in our third example, we're going to look at a kind of a word problem. So according to a study, social robots now outnumber industrial robots worldwide. Social or service robots designed to entertain, educate, and care for human users. In the study, design engineers investigated the trend in the design of social robots using a random sample of 110 social robots obtained through a web search. The engineers found that 62 were built with legs only, 24 with wheels only, 10 with both legs and wheels, and 14 with neither legs nor wheels. So this information is portrayed in the accompanying graph. So we have this graph, and we're gonna kind of work backwards from that in this particular example. So on tab 2.3, I have that basic question. So first, we're going to identify the variable being measured for each of the 110 robot designs. So that is at the bottom here. So there's none, both, legs only, and wheels only. So let's create kind of a way that we can work with the variables. We have none, we have both, we have legs only, and we have wheels only. And we have the values written above, so we have 14, 10, 62, 24. Okay, so based on this, the first question asks us to use the graph to identify the social robot design that is currently used the most. Fortunately, from this visualization, we can see that legs only at 62 is the one that's used the most. The next thing it asks is to compute class relative frequencies for the different categories shown in the graph. So first we need to double check that we've put all the correct number of values in. So if we use the sum function, it will add up these values. Yeah, 110 values of 110, so that matches up. So we know we've got the right info in. Now we want to find the relative frequencies, so we want to find the ratio of each of those categories to the total. So let's call this type, I guess, and this will be the count, and then we want to build out the relative frequency. So the formula is equals the count divided by the total, and double check. I think when you do this question, it's going to ask to 3 decimals. So we want to alter this, and up here in the numbers area, we can make it longer or shorter, but we want to make basically this whole column of relative frequencies be 3 decimal places. So I'm going to edit this formula with the dollar signs to keep that value static, and then we grab the handle, the little square there, and drag it down to get all the other relative frequencies, and we keep it at 3 decimal places. And that is our class relative frequency based on the types. So from that, I think the next part is to create a Pareto diagram, which is basically just a histogram with the largest, that goes from largest to smallest. So let's see, grab these values if it'll let me do it. I want to pull different kinds of charts. Let's go to all charts. I gotta remember where this is. Histogram. Oh, Pareto. Okay, so I insert charts, histogram, Pareto is the second one. I think it's gonna make me have the data next to each other. I want to move these columns around. Try this again. Histogram. There we go. Should create. So Excel doesn't like it if the data is not right next to each other. But this is a Pareto diagram, which is really just a histogram that goes from largest to smallest. So our fourth example, there are currently 6 global credit card companies that allow worldwide usage: Visa, MasterCard, American Express, UnionPay, JCB, and Discover. The company table gives a breakdown on the number of purchase transactions for each company in 2018. Our example for 2.4 is we have the number of worldwide transactions in billions based on each credit card type. So credit card column would be qualitative variables. It's the type of credit card being used. And the number of worldwide transactions would be quantitative data, so that's a accountable value. Now what we want to do is we want to look at what is the relative frequency or the percentage of those worldwide transactions. So what we need to do, like in the other examples, is get the total. So we can use the sum function for our values. So it looks like 295, a little more, billion transactions worldwide. And we want to get the percentage value of each of those. So similar to before, we want to take our count value and divide it by the total to give us the relative frequency. But we want to look at it in percentage value. So first get all the values, and then we can change it to percentage. I believe it's going to ask you just to look at it in 2 decimals this way. So you can look at it as a percentage value instead of as a relative frequency value, and then we want to pull it 2 decimal places. So I'm going to insert a column just to make this easier. Move these values over. I'll call this percentage. And then we can make a chart or visualization off of that. Let's see, which kind of chart does we want? Relative frequency bar graph. So clustered bar graph, clustered column. I like it better in column. So we have a bar graph, and then we want to make a statement about the most used credit cards worldwide. So in this particular example, the most used credit card worldwide would be Visa because it's the highest percentage. And then it would be followed by MasterCard and then UnionPay. Okay, so this is our last example for basic frequencies of data, and then we'll get into summary statistics. So a study recorded data on jamming attacks on wireless networks used by terrorists. In the study, 83% or 83 recent jamming attacks are classified according to their network type, WLAN, WSN, or AHN. I don't know that we even use these particular kind of networks anymore, but probably because they're being attacked. So attacked and the number of channels, single or multi-channel of the network, and the results are summarized in the accompanying table. So on 2.5, we have each of the different network types and whether or not it was a single channel or multi-channel, and we have kind of the count values as well as the total. So on this data, we're going to want to create a Pareto diagram as well as a pie chart for network type only. So first, we need to kind of manipulate the data a little bit. For the first one, all we need to do is get the relative frequency of the each of the different kinds of networks and their number of channels. So same as we've done before, we take the ratio of the count of that particular variable divided by the total. Then going to make that a static cell so that we can copy those formulas down. And let's move this down, make it 3 decimals. Then I'm going to slide this over, insert a column, I guess, and slide our data over. Have our relative frequency, and then we can make a Pareto diagram on this. So we'll go to all charts, it's under histogram and Pareto. So that'll give you the Pareto diagram based on network type and number of channels. Now you actually get to doing this in your homework. I don't believe it's going to make you do it in Excel. I just want to show you how you do it in Excel. So if you run into any problems there, it's just going to show you the Pareto diagram, and you need to select the right one. But going through it in Excel will make selecting the right answer easier, I think. But you probably could just look at the values and determine. Now, the second part of this question, we're going to have to manipulate the data a little bit because we need to kind of merge the multi-channel and the single channel together. So we will do that by adding our W-lon single plus our W-lon multi. And we can do that for the WSN and the AHN. And double check, that still adds up to 83. Now we want to put our relative frequencies for each of those kinds of network types. So we'll have the count divided by the total. Keep our total static. Get those. Let's move this to 3 decimals. And create a pie chart on that. So let's insert recommended chart, and a pie chart is the first one that pops up. So we can see here that when we remove the number of channels variable and only look at network type, that the WLAN local area network was the most attacked, followed by the WSN, and the network that was least attacked was the AHN. Okay. So let's talk about summary statistics. This is going to be all the descriptive statistics that are important. So we can go a long way with a little notation. So suppose we're making a series of observations, n of them to be exact. Then we write, x1, x2, x3. So that's, x sub n. as the values we observe, thus n is the total number of data points, and x4, say, is the value of the fourth data point. So an array is a table of data. So when we're working in Excel, we're actually working with an array of data. And if they get bigger, then we're actually working with matrices. But that terminology is not important right now. So a small set of n equal 5 data points makes the bookkeeping easy. So suppose, for example, we ask 5 people how many hours of television they watch in a week and get the following array. So we have the number of observations and the actual data value. So for each person, person 1 watches 5 hours, person 2 watches 7, etc. So the question we might ask is, what's the center of these data? There is actually several ways that we can look at them. We'll start by looking at just 2. The mean, or the average, hopefully this is something you've heard of before. So the mean or average value is represented by x bar. It's obtained by adding all the data and dividing it by the number of observations. So it's an average. So x bar is the sum of the data divided by the number, or the count, of data points used. So in that data set used, we had 5 plus 7 plus 3 plus 38 plus 7 equals 60 divided by 5 is 12 hours. But based on this example, you may notice 38 seems significantly higher than other people. And so we may be skewing our data higher than it should be because all the other participants were much lower. So that's a possible problem with using a mean. So we have a shorthand for that series, x1 plus x2, etc. It's called it's a Greek letter sigma. You'll see this, and it stands for summation. I don't think we'll get into having to write this out at this level, but the way it looks when you're talking about an average is you have the count, and then we have the summation, which is basically x1 plus x2 plus x all the way to xn. So for each x of I, where I equals 1, so we have x1, x2, x3, all the way till we get to n. So n was 5 in our first example. But just recognize what the different symbols you see. So summation symbol, or sigma. Above here we talk about x bar. Those are all important terminology that'll come up again. So another measure of central tendency is called the median, and it's the midpoint of the data, like the median strip and a road. So to find the median, we take the value of a data set, and we arrange the data in order from smallest to largest, and the median is the value in the middle. Now, if you have an even number of cases or variables, there is no exact middle, so we have to find the average of the two values around that middle. So if the data was, in this example, 3, 5, 7, 7, we have to take the average of 5 and 7 to get 6. And that would give us the median value of 6. So this gives us a general rule, or order the data from smallest to largest. So if the number of data points is odd, the median is the middle data point, and if the number of points is even, the median is the average of the two data points nearest the middle. In this next example, I'm going to show you the formulas in Excel to get those values. Fortunately, it won't require you to reorder the data. So in example 2.6, we need to find the mean and the median. So there's not a mean function in Excel. It's the average function. So equals average, highlight your range of data, and it will give you the mean. And we'll call this x bar. X bar represents the mean. So to get the median, there is a median formula in Excel. Equals median, and we take the range, and In this case, the mean and the median are the same. That's a pretty interesting observation. So we'll come back. So there's one more value that we can talk about. We don't talk about mode that often, but it's the number that occurred most. And you can see in this particular example that the mode is slightly less than the median and slightly less than the mean, which means the data is kind of skewed. If the mean, median, mode were all the same, then it would be perfectly normal data, or unskewed. Let's see. So the relationship between the mean and median provides information about the symmetry or skewness of the data's distribution. So the mean is affected by extreme values, like that 38 we saw in that first example, really pulled the average or the mean up. However, the median was not. The median was closer to what the actual middle value was. So if the data is skewed to the right, then the median is less than the mean. If the data is symmetric, the mean equals the median. And if the data is skewed to the left, then the mean is less than the median. So sorry that's a little blurry, but I think it's because of the way it's been blown up. But those are important things to remember about the kind of relationship between mean, median, and mode. Okay, so in example 7, I believe I put the data in there. Let's see. So we have this set of data. And I think this would be a good time to show you a cool way to get the descriptive statistics. So earlier, I told you how to enable the data analysis tab. I'll do that real quick again. It's in Options, and Add-ins, Excel Add-ins, and make sure Analysis Toolpack is on, and that should make this data analysis pop up. And what we want to use is a cool little tool called Descriptive Statistics. So our input range, if we click this little bar there, or that little arrow, we want to highlight the data that we want to get the descriptive statistics on. Normally you probably have a label on the first row. In this case we don't, but if there was some, like this was, ages of middle schoolers, I don't know, then there would be a value above that, and we would put labels in first row, and that way it would not count that into our descriptive statistics. And we're going to change our output range. I want to put it on this sheet so it doesn't create another sheet or another workbook to put the results in. And then I want to select summary statistics. And so by doing that, now you don't have to type in all the formulas for each of these different things. So it gave us the mean value, standard error, which we'll talk about in a second, median value, the mode, standard deviation, variance, kurtosis, skewness, range, minimum, maximum, sum, and count. So we're about to talk a little bit more about these measures of dispersion. Kurtosis is the fatness of the tails in a distribution, but we're going to talk a lot more about these when we start talking about sampling distributions. Okay, so measures of spread. So besides knowing the central point of the data set, we'd also like to describe the data spread, or how far from the center the data tend to range. For instance, if the students all weighed exactly 140 pounds, there would be no spread, right? The spread would be 0, and the histogram would look very skinny, because it would only have basically one value, a lot of one value. But that's not generally what we see when we see data. So another important concept is the interquartile range. So there's more than one way to measure spread. We're going to talk about standard deviation. We're going to talk about variance, interquartile range. The idea is, in the interquartile range, is we're going to divide the data into 4 parts, or quarters, and we want to see how far apart the extreme groups are. So we want to see how far apart the first and third quartile is because that'll give us kind of like where is most of the data distributed. It'll also help us kind of identify where outliers are in the data that we may want to drop out if we're going to do more advanced analysis on it. So here's the rule, or the recipe, I guess. Put the data in numerical order. We divide the data into two groups, equal high and low groups at the median. The median is a data point included in both the high and low groups. We find the median of the low group. This is called the first quartile, or Q1. And the median of the high group is the third quartile, or Q3, or upper and lower. So the interquartile range is simply the distance, or the number between, if we subtract third quartile from the first quartile, and that gives us the interquartile range. So we'll come back to that in a second. The next thing we want to talk about is the standard deviation. Standard deviation, unlike the IQR, which is based on medians, standard deviation measures the spread from the mean. So you can think of it, roughly speaking, as the average distance of the data from the mean x bar, except that we use the squares of the distance instead. That is, the squared distance of point xi to x bar is xi minus x bar squared. And the average squared distance is this formula. The reason we want to square it is if we were to take a positive value and a negative value without squaring it, we would end up canceling out those values, and it would kind of skew our values. So this is the formula for a population. If we're taking it on a sample, we have to kind of modify that value to account for the fact that it was a sample. So that's where this n comes in. But I'm not going to get down to that level because we're going to use Excel to calculate things out for us. Okay, for this particular data set that we had earlier, 3, 5, 7, 7, and 38, we had x bar, or the mean, equals 12, and we had n equals 5, which was a sample size. If we were to calculate that out, which I'm never going to ask you to do this by hand, you would take each of these values and subtract it from the mean. So 3 minus 12, which is the mean, and we would square it, and we would add it to 5 minus the mean and square it, etc. And then we would have 5 minus 1 as the denominator, because that's part of the formula, and we would calculate that all out, and we would get that the variance is 214. But the problem with using the variance is it's squared, right? And the mean is not squared. So we want to use a different measure of spread called the standard deviation, which is the square root of the variance. And that way it's on the same relative scale as the mean. So the obvious thing to do, and the easiest thing to do, is just take the square root of the variance. Now, there's a very important rule to remember, that the variance is the standard deviation squared, and the standard deviation is the variance, or you take the square root of the variance. So that's a very important relationship between those two values, and you may be asked that at some future date. Just remember that that relationship exists. So standard deviation, you may have heard this term before, is used to kind of tell how far away from the median a particular value is, and we use it because it's on the same scale. All right, so let's see. So this question basically just asks, can you read a sample of data output? So in this case, you need to be able to locate the mean. So the mean on this table is 68.679. Locate the median. The median is 69. Locate the mode. The mode is 63. Locate based on the values of measure of central consistency, make a statement about the type of skewness, if any, that exists in the distribution of these 995 support levels. So the mean is slightly less than median, thus there is little skewness. All right, so variability of data sets. So what is the primary disadvantage of using the range to compare the variability of data sets? The problem with the range is it is rather insensitive to the measure of data variation. So the sample variation, or the sample variance is the sum of the squared deviations from the mean divided by the number of measurements minus 1 to account for sampling error. Population variance is the average of the squared distances of the measurements on all units in the population from the mean. The variance of a data set cannot be negative because it is the sum of the squared deviation. Since we're always squaring that value, we will get rid of any negatives. The variance can be smaller than the standard deviation if the variance is less than 1, because if you square a decimal, then the number gets smaller. Just some kind of underlying rules that you may need to know for homework. Okay, so we've talked about the different kinds of spread. So let's calculate that out in example 2.8. So range. I don't believe there's a range function in Excel. No. So we can take the max value, a set of data, and we can subtract the min value of that set of data, and it should give us the range. Now, we copy the range formula down, but the problem is it's not going to have all the data, so we need to move retype F for H so that it will go the full length of our data. So now we get the full set of range. Makes sense, the max is 7, the min is 0, so 7 minus 0 is 7. So we continue down, we get this one, but once again, we need to modify the formula for column J. So we need to change the H to a J. I typed the wrong area. Try that. This is the one I wanted to change to J. There we go. Okay. That gives us the correct value because we're highlighting that range. You could also retype out each of these formulas if you want, if it helps you learn. But basically, it's just the max minus the min of our set of data. So this goes all the way to column N. So let's modify that. And so it gives us each of our ranges. Now the variance formula, there's several different variance formulas in Excel. I'm just going to use this deprecated one and a previous version of variance because the other ones account for population or sample or whatever, but for our purposes, just the regular var function or variance function should work. So we select var, and it'll give us the variance. Equals var, variance, var, for that set of data. Don't like that it defaults to that one. All right, select that. All right, so gives us the variance. I don't remember how many decimals it wants in your homework. Double check it though. I think only 2. Let's make sure that each of these on the home tab. Let's move this to 2 decimals. Okay, standard deviation. Let's use STDEV. And here goes the standard deviation. Okay. So if we want to check that that formula is working correctly, we could do a square root formula, SQRT, of this. And you can see that the standard deviation formula is really just the square root of the variance. All right, so keep on with that, STGEV, standard deviation, highlight the data. So highlight this data. All right, so that's how you calculate out the range, variance, and standard deviation. So properties of the mean and standard deviation. So the mean and the standard deviation are very good for summarizing the properties of fairly symmetrical histograms or normal data. So I'll come back that a lot of what we're going to learn in this class is based on normally distributed data. So we really need the data to kind of look like what we're talking about. When we get to kind of the assumptions for running, an ANOVA or regression, which is way later in this class, there's kind of an assumption that the data is largely normally distributed. So that's why we're kind of talking about how the spread of data is and the way it is distributed. So another important term that's going to come up when we get to hypothesis testing is this idea of a z-score. So a z-score is a standardized score based on the normal distribution, and it kind of tells us the distance from the mean per a standard deviation. So a z-score of +2 means that an observation is 2 standard deviations above the mean. For the weight data that we used before, we can plot out the data on the original x-axis and find that 2 standard deviations is further out here. Another important rule that we'll talk about later is that, and why 2 standard deviations is important, is that within 2 standard deviations, 95% of the data is within 2 standard deviations. So, but that's more rules that we'll talk about in the future. So, an empirical, we're going to talk about it now. So the empirical rule for nearly symmetric mound-shaped data or normally distributed data, approximately 68% of the data is within 1 standard deviation of the mean, and 95% of the data is within 2 standard deviations of the mean. So that's going to come back in the future. I want you to remember when we talked about this for hypothesis testing, and we get to an alpha value of 0.05, which is the complement to 95%, so 5% statistical significance means something would be outside of 2 standard deviations, which the bulk of our data should be in. So if we find that a critical value outside of that, then that may be of interest to us. So for the weights, our empirical rule holds up pretty well. 64% of the weights are within 1 standard deviation of the mean, and 97% of the weights are within 2 standard deviations of the mean. And we can see this kind of outlier way out here. Okay, so I think we have 2 more examples, and then we'll be done. So example 2.9 is we're going to be given some x values, some standard deviations, and some means. So mu, the Greek letter mu, is what we use for a population mean, and x bar is what we use for a sample mean. And I put this formula over here. So to get our z-score is our x value minus the mean divided by the standard deviation. So sigma is the, kind of looks like an O with a little tail on the top of it, is the population standard deviation, and S is a sample standard deviation. So we're going to find this z-score, and the way we do that is we follow this formula. So if we do equals, parentheses, x minus our mean, this bar, close the parentheses, divided by our standard deviation. So it gives us a z-score of 3. We do the same thing this example. So we have our x value. Put this in parentheses. We have our x value, and we subtract our mean value, u. We divide by our standard deviation. So this would be a population z-score as opposed to a sample z-score. Okay, so same idea for these last two. Make sure you put the parentheses in there because you'll get the wrong answer if you don't. So we have our x value minus the mean for that particular sample divided by the standard deviation. And we got a negative z-score for that one. The last one is our x value minus the mean divided by the standard deviation. And we'll come back to this because we use z-scores, like I said, a lot in confidence intervals and in hypothesis testing when we get to inferential statistics. So this is all kind of very basic kind of terminology and where these things come from and how they're calculated, but we're going to use them a lot more. And with z-tables or with z-scores, we usually get them from a z-table, or I'll teach you some formulas to make it to where a lot of this is a lot easier to do. But we'll get to that when we get to that. So example 10, almost done. So an online provider of global compensation data recently conducted a survey of 1.2 million bachelor's degree graduates with a minimum of 10 years work experience. Of many variables measured by the provider were the graduate's starting salary, mid-career salary, and the college or university where they obtained their degree. A summary of the starting and mid-career salary data was reported. Descriptive statistics were provided for each of the over 300 colleges and universities that graduates attended. For example, graduates of one of the universities had a median starting salary of $40,200 and a median mid-career salary of $70,900. So describe the salary distribution of this university's bachelor's degree graduates by interpreting each of these summary values. Let me see. I don't have that there. But basically, I'll go back here. Based on the data that's mentioned here, we could say the median value was 40,200. This means that 50% of the graduates had starting salaries less than 40,200, right? Because the median salary is the middle point or midpoint. And 50%, the other 50% have salaries greater than 40,200. And we could say the same thing about, the mid-career, median mid-career salary. So 50% of the salaries should be less than 70,900, and the other 50% should be more. Last thing I want to talk about is a box plot. So we talked about the interquartile range. So in a box plot, you have Q1, or the first quartile, or the lower quartile, and Q3, the upper quartile, and that gives us our interquartile range. We talked about that earlier. The median value will be a bar somewhere in the middle. Then you'll have your minimum value and your maximum value as calculated as Q1, or the quartile 1, minus 1.5 times the interquartile range. And this is how, setting this up is how we can find our outliers, or what's significantly outside of the interquartile range enough to be considered an outlier. Now, let's see, go back to a different set of data. I'll just build it off of this. Should be able to insert box plot, box and whisker is what it's called in Excel. So that's what a box plot is based on this data. In this case, we don't have any outliers, but you can see, I don't know if I can make this bigger, the median value is the line in the middle. We have quartile 1 here, quartile 3 here, our min and our max, and that x value is the median from the data. So that's all of this value here, from here. Okay, well that covers chapters 1 and 2. Is there any questions you have or anything else you'd like to discuss before we end the class?
I don't have any questions. It's pretty straightforward.
Yeah, that's good to hear. This is pretty basic stuff. If you're struggling with anything in Excel, let me know. I'll be glad to help you. But we'll get to more interesting things as we get away from basic terminology. So I guess since nobody shows up for class, the remainder of the classes will be virtual sessions because that's a long drive for me to show up here and nobody show up. So I'll post an announcement. We only have 5 more sessions. So like I said, I'll post an announcement about them being virtual sessions.
Okay. Yeah, I did your survey and put on there that I'll be attending virtually because I work there on the campus all day. And
yeah, no, I would. It doesn't bother me.
So
I live an hour and 15 minutes away, but
oh my gosh.
yeah. But no, there's 22 students, and I think only 2 students had filled it out that they were going to show up in person, but it saves me a lot of driving if we do a virtual session. Other than that, I will see you guys next Monday. Hopefully you work on your homework, but like I said, if you want to wait and do it all in 2 weeks so you don't have to pay for the software, I completely understand that. And other than that, I hope this class goes smooth and everybody learns the fundamentals of statistics that they need for future classes.